Okay, good afternoon, everyone. Welcome to Lecture 3 in Fluids 1. So trying a little bit of new technology today. I've got my tablet to annotate with, so we'll switch back and forth a little bit and see how that goes. Hope everyone's doing well. I wanted to pick up a little bit where we left off last time. We spent time talking about Ant-Man last time to drive home the concept of density. Right? And if you weren't there last time, I showed a clip from the 2015 movie from Marvel Studios, Ant-Man. And in that movie, Scott Lang, he becomes Ant-Man. And he puts on the suit that you can see here. And when he presses a button on his right hand, he shrinks down to the size of an ant. And the question we were exploring was, why does Ant-Man need a helmet to breathe? Same with the Wasp from the 2018 Marvel movie, Ant-Man and the Wasp. All right, so let me change over now to annotating. Hopefully this goes well. Practiced a bunch. And okay, here we go. Should be able to share my screen now. Okay. All right. So just bear with me for a moment while I get this set up for the first time. Let me just full screen this so it reaches the whole screen. And go back to annotate. Thanks for your patience. Okay. So revisiting this question of Ant-Man and tying the idea that he needs a helmet to breathe because of relative density into the concept of density. All right. So I'm not a very good artist, but bear with me. We can think about this in the following way. If we draw Ant-Man at regular size, we'll call him Scott Lang. And we'll give him a height of 1.8 meters, right? And then we'll take that length scale, we'll just make a cube around his body. And each side of the cube has that length scale h, 1.8 meters. Okay, in this cube, there are a number of air molecules got this side of the cube here. All right, as I said, not a very good artist. So what happens now? We can think of the density of air at sea level. And that's a little over 1 kilograms per cubic meter. Right? So if Scott Lang's height is 1.8 meters, then the mass of the air in the large cube is rho at sea level times h cubed, right? So 1.225 kilograms per meters cubed times 1.8 meters cubed. So it turns out that in that cube of air around Scott length at full size, there's about 7 kilograms, if I didn't mess up my algebra. We'll just say around full-size Ant-Man. All right, now what happens after he presses the button and he shrinks down to the size of an ant? We're gonna do a zoomed in picture, but basically it's really tiny, little speck. And this time, the dimensions are all, we'll call it little h. And it's about a factor of 140 over h. If you want him to be exactly half an inch high, it's 141.73. H divided by 141.73, that gives you half an inch, which is 0.0127 meters. Okay, so now what's the mass of air in this reduced cube? Let's give him a few air molecules down here, right? Actual density of air is the same, but now for his height, he's got fewer air molecules. So let's say mass of air in cube when Ant-Man is the little size, right? So 0.0127 meters cubed times the density of air at sea level. And we get that it's about 2.51 times 10 to the minus 6 kilograms of air, right? Or 2.51 micrograms of air, okay? Now, if you scale that up, if you think about it, right? Scott Lang at full size takes a lungful of air, gets a certain number of oxygen molecules. Scott Lang, size of Ant-Man, takes a lungful of air, gets many fewer, right? If you were to say, what altitude is that equivalent to? Right? That's how we reach the conclusion that it's almost, at the exosphere, equivalent altitude. Right, so it turns out that if Ant-Man were to reach that oxygen molecule density just by going up in altitude, where the Earth's atmosphere got thinner and thinner, he'd have to go all the way to the thermosphere to get such a relative low density of air surrounding him. All right, so that's Ant-Man. Got one thing. Matthew, I'm having a good day today. I hope that you are too, and I hope that everyone is. All right. This is where we stopped last time, talking about the concept of viscosity. So this is a really key concept in fluid dynamics. We talk about having basic fluid dynamics literacy, this is one where it's really important to understand. It's a little bit subtle, right? So if you think of liquids, water and oil have really similar densities, but they have very different viscosities, right? That's because of molecular interactions and how the molecules can move past each other because of things like intermolecular forces. Okay, so the concept of viscosity is how well a fluid can resist a shearing deformation, right? So we talked last time about normal forces. So if you think of a fluid particle the shape of a cube, the normal forces are perpendicular to the faces of the cube. Shearing forces are those smearing forces, right? So let's define a few things. So shear stress is denoted by tau, and it actually has units of pressure. It's force per area. And then this rate of deformation is lambda dot, not related to the specific gravity that we talked about last time. Okay, so orienting ourselves to this picture again, we've got fluid in a cavity between two plates. You can think of them as infinite plates. One is on the floor and the other plate is on the ceiling. And the top plate is being pulled to the right with a force P in newtons or pounds. Okay. That makes a linear velocity profile develop in the gap here, right? And we'll talk about that more in just a second. A couple other things to note: the height of the gap is B in the Y direction. It's infinite into the page. The top plate is moving now with a velocity of capital U. And we'll talk about this stuff in just a moment. Let's talk about this linear velocity profile. It develops a linear velocity profile. And if we look at the boundary conditions, we know that at the bottom wall, which is not moving, the velocity of the fluid has to be 0 by the no slip condition. So U at Y equals 0 by no slip condition. This is a really important concept. We're going to use this all the time. Basically, anytime a fluid is in contact with a wall, a solid wall, it has the velocity of that wall for the purposes of this class, right? And then of course at the top, the fluid here has the same fluid as the plate, also by the no slip condition. So the fluid velocity up top is capital U, down bottom is 0. If you imagine examining a little square particle of fluid, let's draw a picture. It's experiencing a velocity of U at the bottom, whatever it is at that height. But then at the top of the particle, it's U plus du dy times delta y. And that's because we've got that linear increasing velocity profile, right? Okay, now what if we take our cube to be the entire height of our channel? So we'll draw our cube again. So now we're going to identify this point A and this point B over here on our cube. So this is at time equals 0. And now a small infinitesimal amount of time passes. And we've got the same cube at t equals delta t. And the same cube now is sheared by the action of that top plate, right? And so the point A has migrated, or pardon me, point A has stayed where it is. The point B has migrated to B prime, right? And the fluid has also rotated a bit. It's sheared, right? And this wall has rotated through the angle delta theta, okay? This top plate has translated through, we'll call it delta A. Okay, now we've got that set up. A couple other things I want to mention, of course. We talked about how we have a linear velocity profile here. That means that u, little u, in this gap is a function of y. All right, so what do we want to say here? We're talking about this concept of viscosity, how much a fluid resists shearing forces. If it resists a lot, it has high viscosity. If it resists not very much at all, it has low viscosity. Well, the very definition of a fluid is how the shear stress is proportional to the deformation. We'll talk more about that in a second. But let's take this quantity, rate of deformation, gamma dot, and let's define it. So technically, gamma dot is the limit as delta t goes to 0 of this angle that the side of our fluid particle rotates through in time delta t over delta t. Okay. And for a Newtonian fluid, and in this case here, it's identically equal to du dt, right? So the velocity profile in this gap, its derivative with respect to time. Now the very definition of a fluid, I'm going to write this in red because it's important. For solids, we'll say that our force is proportional to the deformation. For fluids, our driving force is proportional to the rate of deformation. Right? So huge fundamental difference between solids and fluids. If you think about the very simple law that defines a solid, you can think of a linear elastic solid like that obeys Hooke's law, right? Let's think about a spring, right? The force, the resisting force in a spring is linearly proportional to the amount that the spring is stretched. In a fluid, the resisting force, tau, the shearing force, is linear proportional to not the amount the fluid moves, the rate at which it moves, right? Is the fundamental, I'm gonna box this, it's so important, the fundamental difference between solids and fluids. Okay. Now I have one more thing to talk about. And that's the definition of a Newtonian fluid. So for a Newtonian fluid, which almost all the fluids we talk about in this course will be Newtonian fluids, tau is linearly proportional to du dt, or linearly proportional to gamma dot. I'm going to box this in red too. And the constant of proportionality is the viscosity. So for a Newtonian fluid, this formula here holds, and mu, our dynamic viscosity, is a constant, okay? For the purposes of this course, this formula is almost always true. Unless it says you're dealing with a non-Newtonian fluid, right? There'll be a small part of the course where we talk about non-Newtonian fluids, and then you can't assume this. But if it doesn't mention that a fluid is non-Newtonian, you can always assume that tau, the shear stress, is linearly proportional to du dt, the vertical Oh, pardon me. Got a little typo here. Woo. This should be y. du dy, pardon me. Okay. Is linearly proportional to the change of the velocity in the direction normal to the wall. Okay. So let's talk about viscosity. Hold on, I've got somebody in the chat here. Yes, can I explain again the difference between solids and fluids through the equations in the box? Sure, absolutely. Thank you for asking. Okay. So in a solid, the resisting force, the internal resisting force, is linearly proportional for a simple solid. Well, we're just talking about simple fluids and simple solids here. But in a solid, the resisting force internally is proportional to the deformation itself. In a fluid, the internal force that resists is linearly proportional to the rate of deformation. So not how much a string is stretched like it is for a solid, but the rate at which it stretches. Does it stretch really fast, right? Or is it really hard and slow to stretch, right? So for a solid, you've got tau is proportional to just the deformation itself. In a fluid, fundamentally, you have the internal resisting force is proportional to the rate of deformation. So high viscosity, low viscosity deformation. Okay, great. Glad you got it. Okay, and then Matt is asking, is the definition for gamma dot still du dt? Yes, it is. I want to get through the lectures today, so I don't want to derive that, but that is correct. You can read the viscosity portion in the textbook. It's section, I want to say 1.7. It's part of your assigned reading for chapter 1. But these formulae are correct. Okay, so let's talk about dynamic viscosity, which is mu, which is the one that shows up in this formula for Newtonian fluid. And so for water, oops, sorry, accidentally scrolled there. So for water, it's 1.12 times 10 to the minus 3 Newton seconds per meters squared. I'll just give it in SI units for now. And then for air, the dynamic viscosity is 1.779 times 10 to the minus 5th Newton seconds per meter squared. And you can look up these values in tables 1.5 through 1.8 in the textbook. Really, really handy. You're going to refer to these tables all the time in this course. So if you are one of the few people who has a physical copy of the textbook, you'll find them on the inside flap. But if you've got the electronic, cheaper electronic version, you can just click right to these tables. All right, and then for water, water is 1.12 times 10 to the minus 6 meters squared per second in kinematic viscosity, and we'll talk about the difference in just a moment. And air is 1.46 times 10 to the minus 5 meters squared per second. So you can see the units of dynamic and kinematic viscosity are different, right? Dynamic viscosity has force times time per area. Kinematic viscosity is area over time. So if you can think about kinematic viscosity, you can imagine pouring a blob of fluid onto a plate, and you can measure the viscosity by how long it takes, how many seconds it takes for the fluid to cover a certain area. All right, and then what is the definition? Of course, I'll write this in red too, because it's really important, of kinematic viscosity. It's just the dynamic viscosity divided by the density. Okay. And so sometimes it's more convenient to use kinematic viscosity, sometimes it's more convenient to use dynamic viscosity. Let me check in with chat. Okay. Great. All right, let me save that before I forget. Okay. Okay, so now let's get into some examples. So here we have the same setup that we had when we talked about the concept of viscosity on the last slide, but now we're going to work through an example with some values. Okay, so we've got our two flat plates again. We've got this linear velocity profile set up between the still bottom plate and that top plate that's being pulled with a force P and is translating with a steady velocity, capital U. So there's crude oil in the gap now, and it's given, the viscosity is given in British gravitational units. And the question is, if the gap height is 0.1 inch, what value of that force P is required so that U, the velocity with which the plate translates, is 3 feet per second, right? And then it gives the effective area of the upper plate, and the area we're talking about is the entire area that's in contact with the fluid. So if you were actually looking down on the top plate, it would be that projected area. Okay, so whenever we're talking about shearing forces that we get from shearing stresses, we think about how much fluid, the area that's in contact with fluid, and multiply by that area. So if you've seen anything like aerodynamics before and you use a frontal projected area, that's not what we're doing here. Okay, so how do we start to think about this problem? Basically, it's a sort of a statics problem. I mean, it's moving. It's a dynamics, a simple dynamics problem, right? So you're pulling a plate to the right, and you want to know, given this particular fluid, how hard do you have to pull to get it to translate that at that speed? So we can do our sum of the forces in the x direction, set them equal to 0. Let's draw our little free body diagram. And what do we have here? We've got P, we're pulling the plate with the force P. And then here we've got the shear force. So this is not the stress, this is the shear force. So we'll call it F sub tau, resisting that motion. And we're just gonna, of course, say the sum of the forces in the x direction is equal to 0. Okay, great. We need to find P, that's not given. They're asking us what value of P. Do we have tau? No, it's not given, but we can calculate it with what we just learned about Newtonian fluids. We're gonna assume this fluid is Newtonian because they haven't hinted that it's not. And we've got the area of the plate. So let's go ahead and use that Newtonian fluid formula that we just learned on the last page and solve this problem. Okay. So if we assume the fluid's Newtonian, then we've got that wonderful formula. So we've got our linear velocity distribution here. And that velocity distribution has got to be little u of y equals big U times y over b, right? So big U is the velocity with which the top plate is translating, y is the height that you're at in the gap, and b is the height of the gap, right? And so let's just do common sense check here. If this is true and y is equal 0, we're at the bottom plate, the velocity is 0, yes, right, by the no slip condition. That's correct. And then let's just common sense check. If we plug in y equals b here, we should get back capital U, and we do, right? Okay, now we need to say du dy. We need to calculate du dy. So that's pretty straightforward. It's just d by dy of capital U y over b, and that's just capital U over b. Great. Okay, so now we can calculate tau. So tau is equal to our viscosity, which the value is given, 9.52 times 10 to the minus 4 pound second per feet squared. Times, sorry, I'm skipping lines here, times 3 feet per second, which is our capital U, over 0.1 inches, right, which is our B. And then we've got to do a conversion, units conversion, right, because we've got 12 inches is 1 foot, because we've got inches here for our length scale, but our viscosity involves feet. So we've got to do that conversion. So in the end, we get 0.343 pounds per feet squared. Oops, just said cubed. Let's do squared. Is our tau, is our shear stress. Okay, wonderful. Now we're almost done. What value of P is required, so we can pull this all together now. So we saw if we sum our forces, we've got P is equal to tau times A, right? That's our, when we sum the forces in the x direction, set them to equal to 0, which we should because it's translating without acceleration. So now P is equal to tau times A. So it's 0.343 pounds per feet squared times, we were given 200 inches is the sort of bottom surface area of that top plate. If you're projecting looking down, all the plate that's in contact with the fluid. And then of course we've got to convert from inches to feet again. So we say that 1 square foot is 144 square inches, and we get 0.476 pounds is the force with which, whoops, is the force that you need to use so that that top plate translates at the given speed, 3 feet per second. All right, any questions about that? No, wonderful. Let me just do a quick time check. Oh my goodness, all right. I think I'm going to have to leave the rest of the examples for Hyungan's problem solving session on Friday, because for some reason when I teach this class online, everything takes 3 times as long. So let me go ahead and save that. And I'll let Hyung do this example on Friday. And we'll just talk a little bit more about viscosity. So what have we learned about viscosity so far? I got one question from a student. It was, do we have to remember any constants? You don't have to remember constants. You can find them in tables 1 through 5 through 1 through 8 in the textbook. And you'll refer to those values, especially density and viscosity for water and air at standard conditions. You're going to refer to those values all the time. You probably will end up memorizing them, but you can always look them up. Okay, I'm going to go back to screen sharing over here on my desktop and skip ahead to where we were on the tablet. Okay, so we've now derived this formula, and the formula is tau, the internal shear force that resists flow, is linearly proportional to the vertical velocity gradient in a fluid, and the constant of proportionality is mu, the viscosity. So you can have different fluids, right? Last time we watched Ray's video from homework 1, he poured honey into a cup and he poured juice into a cup and he compared a really great demonstration. You know, honey really resists that shearing force provided by gravity a lot. And so it takes a while to get it pouring, whereas the juice just pours right out. It's got a much lower viscosity. That's that link up there. Right, so different substances obviously have different viscosities. So if you think about our formula, tau equals du dy times mu, the slope of these different lines for these different fluids is mu, right? So here for crude oil, we've got a very high viscosity because we've got a very steep line, right? So high slope. Water has got an intermediate value. If we heat water up, it gets less viscous, right? We get lower slope. And then air has got an even lower value. Okay, keep in mind that the viscosity of the same substance, as you see here with water, changes with temperature, right? And also with density, but we won't talk about that too much in this course, right? So here we've got our viscosity, our dynamic viscosity mu as a function of temperature, and you can see how it changes for different substances. So air, is not too affected by temperature changes. The viscosity is pretty stable, same with hydrogen. So those are our two gases we're looking at here. Water, you get a significant reduction in viscosity when you heat it. And then if you look at these oils, SAE10W and glycerin, you get a pretty dramatic reduction in viscosity with temperature. And let me just see, I've got someone messaging me. Yes, really great question. Because those lines are linear, does it mean that they're Newtonian? Absolutely, yes. So good, you're actually getting ahead to what I want to talk about in a moment. Okay, so now I want to talk about Newtonian versus non-Newtonian fluids, right? So what happens if you have a fluid that the viscosity actually changes with tau, with the shearing rate? Then you've got a problem. Then you can't assume that mu is a constant, and you don't have a linear relationship between tau on the left-hand side of the equation and du dy on the right-hand side of the equation, right? Because that viscosity now is a function of tau. So I'm going to actually show you a really fun video about oobleck. And before I do that, I'm going to launch a poll and just ask to see how many of you have heard of oobleck. This will just take a moment. So just go ahead and just let me know how familiar you are. If you've ever heard this term before, or you've heard of it vaguely, but not really sure what it was. You've heard of it, you know what it is, but you haven't really dealt with it hands-on. Okay, oh, this is interesting. So we've got pretty much people who have never heard of it and people who have done experiments with it. That's great. I'm gonna end the poll because we're at 94%. And so you can see majority or the largest option, never heard of it before today. Second largest, I've not only heard of it, I've seen it, performed experiments with it, right? And then a couple other options in the middle. Okay, so for those of you who have not heard of oobleck, it's really fun. It's a non-Newtonian fluid, and let's check it out.
Dr. Staples,
my favorite oobleck video.
I don't think you switched to your desktop. I think you're still sharing the Beam annotator screen.
Oh no. Okay. I think I've got to stop sharing over here. Thank you for letting me know. So it says on my desktop that I am screen sharing, but it doesn't seem to be working. So let me try and stop over here. Hmm. Are you still seeing my annotator?
Yeah, yeah, still the PDF annotator screen.
Okay. Sorry, I test ran this before before class, but now having a different issue. I think I'm gonna have to kick annotator out of the meeting to be able to do this. Let's see. All right, I withdrew its co-host permission. Let me stop sharing and reshare on my desktop, and hopefully that will take care of it. All right, what are you seeing now?
So it looks like if we go up to view options, and we can actually choose if we want to see your screen or the beam annotator. So I think I now see your desktop. I don't know if everyone is on your desktop right now.
So let me just ask people, can anyone not see my desktop? So right now what I've got open is a YouTube frame, and I'm about to play a video called Can You Walk on Water? Is there anybody who can't see that? Okay, so there's at least one person who can't see it. So let me kick Beam Annotator out of the meeting. Hopefully that will solve it. Okay, quite a few people who cannot see it. Thanks for your patience while I try and sort this out. Okay, I have stopped Beam Annotator and I'm sharing my desktop. And hopefully now everyone is seeing this YouTube frame with a girl in a white tank top, and it's a video called Can You Walk on Water? Is there anyone who can't see that? All right, awesome. Looks like everybody can see it. Here we go. Oobleck. Okay, so oobleck, as you can see, is super fun. And it's a non-Newtonian fluid. It's made from cornstarch and water. And it has the property that if you apply a really low shear force, it behaves as a liquid that flows really easily. If you apply a really high shearing force, it freezes up and behaves like a solid, right? And so that's why you see people can basically walk on it if they run, if they walk fast enough, and if they're really transferring a very large impulse to the surface. You saw the last part of the video, people were a little bit shy, a little hesitant, not really applying large forces, sort of tiptoeing across, and they started to sink in, right? So oobleck is what's considered a shear thickening fluid. So now when you look at these non-Newtonian fluids and you look at their behavior, when you look at tau, the shear stress, versus du dy as a function of du dy, for Newtonian fluids, all these lines start at 0, tau equals 0, and they're straight lines, right? Because the viscosity is constant. For a non-Newtonian, you can think of it as a non-constant viscosity with a non-constant slope, right? So these lines have a non-constant slope. So here, oobleck falls on this type of line. It's shear thickening. So if you apply just a little bit of stress, you basically have you basically have not much response at all, right? And then it behaves in this way, where if you apply enough stress, you've got a really large rate of strain, okay? Shear thinning fluids do exactly the opposite, right? So when you apply just a little bit of stresses, shearing stresses, they flow really easily. When you apply a lot more, or pardon me, they're very solid, very hard to move. When you apply a lot more, they start thinning. So I was going to do breakout rooms, but as you can see, we're almost out of time. So I just want to open the floor up now instead of think, pair, share. I want to see if you guys can think of an example of a non-Newtonian fluid that's shear thinning. So something that when you apply just a little bit of shearing stress or force, it doesn't flow very easily. The more force you apply, the easier it flows. Okay, so we got Leith says ketchup. That's a great classical example. Can anyone think of another example of a shear thinning fluid? So maybe something that you wouldn't necessarily think of as a fluid. Paint. Okay, yeah, there are some paints that behave this way as well. Great example. Toothpaste. Right, yeah, exactly. So toothpaste, you squeeze it onto your toothbrush and it seems solid, right? It just sits there like a blob. It looks like a solid, but then of course you apply the smallest amount of shearing stresses by rubbing it on your teeth and it starts to flow really easily. Another great example is quicksand. You might not think of quicksand as a fluid, but it behaves as a fluid. Concrete powder, yep. Another great one. It does behave as a fluid. So if you think about quicksand, you know, from all the cartoons we watched growing up, the classic cartoon example is a character steps into quicksand and says, oh no, it's quicksand. And then they start struggling and then they just start falling into the quicksand, right? So that's exaggerated. Apparently it's not even possible to drown in quicksand. But it is true that the more you struggle, the more shearing forces you apply, the more liquid-like it becomes. So I think we need to stop there for today. We'll talk about this next time. I'll have Hyungan going over this. I just want to stop by mentioning a few things. I want to end with mentioning a few things for next time. So a couple of big announcements. So Hyungan, our TA, our excellent TA, who does really wonderful fluid dynamics research. If you remember from the first lecture, he does that splashing droplets on leaves research. His office hours begin tomorrow. Now remember that your homework is due on, midnight on Sunday. And so we've got a lot of TA office hour support at the end of the week. So hopefully you have a chance to look over your homework and then ask questions during this time. I got a question was, is the quiz timed? No, this quiz is not timed. And in general, the quizzes are not timed. Hyungan has office hours tomorrow, 8 to 9:30. Sorry for the early time slot, but like I said, I was looking at your schedules and there are big classes that a lot of you are in and we wanted to avoid all those classes. And he also has an office hour. Yes, the homework is through Wiley. He also has one Thursday, 1 to 3 p.m. The homework is through Wiley. So if you have an issue, you haven't purchased your Wiley yet, your access, or you're having some sort of issue with Wiley, try to get that cleared up as soon as possible. I don't have homework 2 finalized yet. So because I saw that we were sort of getting off schedule compared to how I usually teach this week. I haven't finalized and hit share on the homework yet, but I'll do that by the end of the day today. This Friday, you've got your problem solving session with Hyunggong on Zoom. The due date is Sunday. So someone asked, can we move the due date to Sunday? It is on Sunday. Is there a course code for Wiley? So you access Wiley Plus through Canvas, and when you click to access it, it already has the course code information. So you just have to follow the instructions to go ahead and purchase Wiley Plus access. I don't know exactly what that looks like because it looks different from my end. But if anyone is willing right now to drop their name in the chat for someone who'd be willing to answer questions about what it looks like on the student end. Oh, okay. So Christian's saying that the class is not viewable to him in Wiley. Okay. All right. So when you go in through, we've got our, okay. All right, well, that seems like a huge problem. We're a minute over time. I want to be respectful of your time, but I'm just becoming aware of this issue that you can't view the class. Can anyone view the class when you go in through Canvas and you click on the modules? So is anyone able to go in and access Wiley Plus? No, okay. All right, so this is the first time I'm hearing that, so I apologize. I'm gonna look into this right now, and I'll get it sorted out as soon as I can. And obviously, I wasn't aware of this issue, so I'm happy to push back the quiz and homework due date if people would find that helpful. All right, any last things you guys wanna mention before we hang up? You're free to go now, but if anyone wants to stay and ask questions, please do. All right, so a couple of people are hypothesizing. Thank you, everybody. Have a good day. A couple of people are hypothesizing that after homework 2 is published, that the Wiley course might be accessible. I'll try that as soon as I can after I finish selecting the problems, and we'll see if that fixes it. Anything else that you guys wanted to bring up? All right, thank you very much, everybody. Have a great afternoon.